My name is Brendan Allen, and I'm presenting the paper titled Adaptive Trajectory Tracking During Motorized and FES-Induced Bicep Curls via Integral Concurrent Learning. My co-authors are Kimberly Stubbs and Dr. Warren Dixon. Throughout the world, there are millions of people who suffer from various neuromuscular disorders, which cause difficulty or an inability to control one's own muscles. These disorders have numerous causes. For example, there's stroke, Parkinson's disease, spinal cord injury, cerebral palsy, and there are many others that would take far too long to list. Needless to say, neuromuscular disorders are a huge problem. In a healthy person, the central nervous system, which includes the brain and spinal cord, sends information to motor neurons throughout the body, which generates action potentials to cause muscle contractions. Depending on the disorder, some part of this mechanism does not operate properly, which may result in movement disorders and a lower quality of life. To combat these disorders, a muscle can be artificially contracted with functional electrical stimulation, or FES. FES uses an electrical current that is applied either internally or externally to replace the initiation of an action potential to perform a functional task. However, there are numerous challenges associated with closed-loop FES control. For example, there are uncertain and nonlinear dynamics, and switching control between FES and a motor requires a switch systems analysis. Another critical challenge is fatigue, which practically reduces the duration of an exercise and may hurt rehabilitative outcomes. The focus of this talk is the development of a closed-loop control system for a motorized and FES-induced biceps curl exercise using integral concurrent learning, or ICL. Practically speaking, ICL has numerous benefits. For example, ICL allows for unknown parameters, such as person-specific parameters, to be identified in real time. Further, adaptive controllers such as ICL allow for more efficient control designs, which may improve comfort and reduce fatigue, which can improve the rehabilitative benefit of the exercise. The major contributions are that this is the first ICL controller implemented on an FES system, and data-based opportunistic learning is implemented to learn the parameters of each subsystem. Now let's look at the arm robot dynamics. The dynamics are comprised of a human input torque, which are from the FES-induced muscle contractions, a motor input torque, inertial effects, gravitational effects, viscoelastic tissue effects, which are both force length and force velocity dependent, and finally damping effects. The control torques can be further expanded as shown, where the torques are comprised of a control effectiveness term and a control input term. We can now expand the control inputs further. The control inputs are comprised of a control gain, a switching signal, and a control input. The switching signals are defined as shown, such that stimulation occurs during elbow flexion and the motor is applied during elbow extension. Using the previous definitions, the combined arm robot dynamics that are shown are obtained, where the following terms are defined. The motor effectiveness is assumed to be known, whereas the muscle effectiveness is assumed to be unknown, which leads to a different approach for the FES and muscle subsystems. An important assumption of the system is that the dynamics are linearly parameterizable, such that when the motor is active, we obtain the following, and when the FES is active, we obtain what is shown. Note that the theta terms represent the unknown and constant parameters. This paper has two control objectives. The first is trajectory tracking, and the second is to estimate the unknown parameters of the system. The first control objective is achieved by defining a position error and an auxiliary error system. The position error is the desired position minus the measured position, and the auxiliary system is comprised of a cadence error and a position gain. Taking a derivative of the auxiliary system and substituting in the dynamics yields the shown open-loop error system, where the term y2 is obtained from the shown equation. The second control objective is achieved by defining an FES parameter estimate error and a motor parameter estimate error. The parameter estimate errors consist of the actual parameters minus the parameter estimates. The FES and motor parameter estimates are shown. Notice that a different update law is implemented depending on the current subsystem, where one subsystem is when the motor is active and the other is when the FES is active. Typically, parameters of a given subsystem are only updated when in that subsystem. In fact, the highlighted terms represent the adaptive update terms of a typical adaptive update law. However, in this paper, ICL update terms are included in the update law as shown. The highlighted switching signals are defined to indicate when sufficient learning of the parameters has occurred. Thus, once sufficient learning has taken place, the parameters are able to be updated for the remainder of the experiment, which allows for exponential results to be obtained. Let's break down the parameter update laws further by considering the FES parameter update law. The FES history stack is defined as shown. Further, the FES ICL terms are defined as shown. However, it is not desirable to include the data with zeros in the history stack, and so the following definition is made. Notice that from this definition, only the highlighted data is included in the history stack. Thus, the history stacks include prior input and output data. And an important observation is that the highlighted terms are equivalent. The term on top is the implementable version of the history stack, and the term on bottom is the non-implementable version that is used in the stability analysis. As a brief aside, it should be noted that a benefit of ICL is that the dependence on acceleration can be removed. Recall that we had previously defined the shown terms, which are seen to be functions of the acceleration. However, integrating both sides yields the following. Again, recall that the FES and motor update laws use the integral of y1, which can be seen to not have any dependence on the acceleration. Based on the stability analysis, the following FES and motor controllers are defined. Substituting the FES and motor controllers into the open-loop error system yields the closed-loop error system. A common Lyapunov function candidate is defined as shown. Recall that the control objective is to achieve trajectory tracking and parameter estimation. Therefore, the trajectory tracking and parameter estimate errors are included in the Lyapunov function candidate to be able to show that these errors are bounded. The Lyapunov function can be bounded by the following bounds. Theorem 1 looks at the case before sufficient learning has taken place for both the motor and FES subsystems. Let t be defined as a known positive constant that refers to the instant that sufficient learning has occurred for both subsystems. Theorem 1 then states, for the closed-loop error system, the control system yields bounded trajectory tracking and parameter estimation errors over the time interval 0 to t, provided the shown gain conditions are satisfied. Further, Theorem 2 now refers to the time after which sufficient learning has occurred for both subsystems. Theorem 2 first considers the time from t to infinity and then combines the result with Theorem 1 to obtain an overall result for all time. Theorem 2 states, for the closed-loop error system, the control system yields exponential trajectory tracking and parameter estimation errors over the time interval 0 to infinity in the sense that is shown, provided the gain conditions from Theorem 1 are satisfied. The proofs for both theorems are included in the paper. As an initial validation of the control system, a simulation was performed. For the simulation, a sinusoidal trajectory is tracked to represent performing bicep curls. The tracking errors are shown. Notice that the errors start out initially poor, but improve with time. Now the control inputs can also be seen. The parameter estimates are now shown, and notice that the parameter estimates quickly approach the actual parameters. And lastly, we can see the learning terms. The parameter estimate errors improved as the value of the learning terms increased. In conclusion, a data-based ICL controller was developed for a switched motorized FES-induced biceps curl exercise. This is important because it results in a more efficient controller, which may reduce fatigue, and it allows for person-specific dynamics to be identified in real time, which could have a clinical significance, such as potentially identifying certain conditions. Future work will include performing experiments to further evaluate the developed control system. Thank you for your time, and if you have any questions, please email me at brendancallen@ufl.edu.